Konnichiwa. You know that little blinking box in your house? Your router? Ever wonder what's really inside it? Our first speaker, Justus Wilhelm Perlwitz, definitely does. He's a vulnerability researcher who loves digging into these MIPS-based devices. His talk is all about QEMU and AFL++ fuzzing. He's going to show us the methods he uses to fuzz these quirky little boxes, hunt for bugs, and get around all their weird hardware. This is real-world, hands-on hacking. Let's give a warm welcome to Justus Wilhelm Perlwitz.
Hey, how's it going? I'm really happy to see a lot of people here. I know it's a Friday. Everyone has to work, and still, you're taking the time to see my talk. That's great. And I would like to talk, thank you for the great introduction as well, about something that I've been working on for quite a while now. And if I didn't talk about it, all those results will be for nothing. もちろん日本語でも何か質問があったらたくさん聞いてください。So, we're going to talk about what you can do with QEMU and AFL++ for this little fella right here. So I'll introduce what the general problem is that we're going to solve today, and I'll talk a little bit about this fella right here, and then we're going to see how we can apply AFL++ to this, and then maybe even get a CVE out of it. Who knows? Let's get started. All right. Is it doing something? No. I want you to, how do I show a full, well, let's just, wonderful. Okay, great. So we have two learning goals for today. Number one, and this is really important, this is about emulating firmware. We're not testing the real deal, because when you emulate it on your computer, you can do so many more things, so much faster. That's why you're going to learn how to make a mock environment for it. And because, again, the talk is about AFL++ and QEMU, we're going to see how to take this mock environment and the firmware and then make it play with AFL++ and QEMU. How do I, this is embarrassing. How do I make it show full pages? View, single page. Wow, there we go. Oh, wonderful, great. So a problem that you'll have when you want to fuzz things that run on proprietary hardware is, first of all, you only have one of those devices. Now, of course, this one is pretty cheap, so you could think about maybe buying 10 or 20 and just send requests to them, but then you're going to need a lot of cables, and who wants that? Also, I'm not originally someone who hacks stuff. I'm a software developer, so I like to apply software development skills to my day job. And the other thing is, this isn't particularly fast either. So we want speed. Not only do we want to fuzz hundreds of these, we want to fuzz really fast. And then the third problem is, so you found a crash, and you gotta plug out the cable, plug it back in, wait a minute for it to boot up, and how do you even know that you're going to be able to reproduce it? Maybe the bug that you triggered changes something in the device, so you want a sort of, well, reproducible environment. Same configuration, everything the same. That just makes your life a lot easier, especially if you find a vulnerability and you want someone else to be able to reproduce it as well. Great. My talk will introduce 4 steps that I think can serve as a blueprint for you getting started with fuzzing MIPS routers. So the first step that I'm going to talk about is how do you even know what you're working with? So we're going to take a closer look at the hardware and also the firmware, see what's running on there. And then the second step would be to reverse engineer this firmware and understand what dependencies it has, and we'll then start mocking that. So I'm going to talk about a lot of strategies for mocking here as well. The third step is to actually set up the fuzzer, because mocking alone is not enough. You need to let AFL++ know, like, this is how you work with it. And then once you've done all of that, probably 95% of the work, you can fuzz it for a little bit and then immediately find something. That's probably the best part about fuzzing, is that the setup is most of the work, and then when you do the setup well enough, you'll immediately find results, especially for MIPS hardware. Wonderful. Let's get started. And I think for those who aren't so familiar with fuzzing here, I think I've been throwing around a lot of words. I'm sure everyone will appreciate a little background on fuzzing, emulation, QEMU, and so on. So in general, all a fuzzer does is give your program a lot of random inputs, and you cross your fingers and hope that it crashes. And it turns out that there's quite a few methods to doing that efficiently, and that has to do with how you pick those random inputs and how you observe the state of the program after you give it inputs. And of course, another problem is if you just start randomly feeding inputs into your program, you won't find a crash for a really long time, maybe. So how do you know from all those random naughty inputs that you're giving it that you're getting closer to finding a crash or you're not close at all? So that's what good fuzzers try to solve for you. Now, my favorite fuzzer is AFL++, but before AFL++, there was AFL. And of course, before the fuzzer called AFL, there's this really cute bunny right here, and I think we all hopefully like bunnies. Yeah, good. Okay, wonderful. So AFL is named after the American fuzzy lob. It's a cute bunny. And I think the important takeaway for what makes American fuzzy lob, AFL, as a fuzzer so special is it's really good at looking into your application that you're fuzzing by doing something called instrumentation, meaning it can add a lot of code, like special instructions, into your application that will then tell AFL++ or AFL what the application did after you gave it certain test inputs. And another thing that's really cool about AFL and AFL++ as well is that according to this instrumentation and coverage information, it uses various algorithms, including genetic algorithms. I have not really looked at the source code, but it sounds really cool. It uses all of that feedback to then make really cool inputs. And another thing, again, that I find very useful about AFL++, and that was not the norm in fuzzers before that, it doesn't only consider crashes as something that is interesting, but it also has a notion of, it's called interesting test cases. And the idea there is that if you give your program some input and it starts calling functions that it hasn't called before, then AFL will be like, aha, we haven't encountered that before. I should send that program more input to get more of that behavior. So AFL is really trying to cover your whole program, trying to give it all kinds of interesting inputs, and most of all, you're not treating your program as a black box. They call it gray box fuzzing, so you're trying to look inside as well in order to see what it does specifically. And AFL++, so AFL is more or less not maintained anymore. AFL++ started as a collection of patches and improvements, and it's the current version of AFL that you can use right now. It's still updated. I also started contributing to it this year, and if you want to do fuzzing with AFL in 2025, next year, 2026 too, AFL++ is a good choice. Now for emulation, I would like to talk about emulation a little bit, just to mention the difference to virtualization, for example. So the main problem with a router like this is that it runs a different CPU. It has a different CPU architecture. So in particular, this one is called MIPS, and I'll talk a little bit more about MIPS later. And the computer that I brought today, for example, has an ARM CPU, and many of you will probably have a computer that runs x86 or x64, so Intel or AMD, for example, CPU. So they all have different instructions, and they're not compatible with each other. So even if you have a Linux binary, you can't just run it on any machine if they are compiled for different CPUs. And with an emulator, you can do this. So they bridge the gap. And yes, in the end, we will see that QEMU solves a lot of those issues. And very importantly here, we're not creating a virtual machine. We're almost like just letting the thing run on your computer as if you're just running any random program. And specifically QEMU, many of you probably know about QEMU, the virtual machine, and possibly some of you also know about the user space emulation. I wasn't so aware of the user space emulation feature that QEMU has, and now I've started using it a lot because it turns out it's extremely useful. So you can take any binary for any CPU architecture, and as long as it's compiled for Linux, meaning it uses the system calls that Linux provides you, you can just run it on another Linux OS machine, and it will more or less not know the difference. And of course, since this talk is about the difference, we will talk about how to bridge all those unique features of this hardware so that you can really run it anywhere and it won't make a difference. What I particularly like about QEMU user space emulation is that it is meant to be able to run QEMU user space emulation. So you can, I don't know if that makes sense, you can run QEMU user space emulation compiled for MIPS, for example, on QEMU user space emulation on your machine, and then emulate a third CPU architecture's program. So that's pretty cool. I mean, that just tickles my brain in funny ways. And for QEMU specifically, another reason why we're using it is because it integrates quite well with AFL++. Right, one more thing I should mention here. So I'm reverse engineering and fuzzing firmware that I assume will not hurt my computer, but if you start running programs with the QEMU user space emulator, it will run as a regular binary on your computer. So it can do anything that any other binary can do as well. So it's very different from running an app in a container, for example. There's no sandboxing or anything. So that's something to watch out for. Please don't start just blindly running binaries with QEMU user space emulation. Wonderful. To get a general picture of how AFL++ and QEMU work together, I've already mentioned there's these interesting inputs, the crashes, and so on. Well, what we're trying to do is we have this QEMU runner right here that runs some binary that you want to find bugs in. QEMU uses its scheduler to find really interesting inputs, feeds that into the QEMU runner, and depending on the outcome, it will do different things. And we'll see what those things are, and I will get into this later one more time. So to sum it up, the AFL++ architecture in combination with QEMU, there's 5 parts that we care about today. Here's a mutator, so this is creating interesting inputs. There's a scheduler. This chooses those interesting inputs because we have to keep in mind that even if we run this on a really fast machine and we start fuzzing things, there's still a certain amount of fuzzes that we can do per second, so we still should prioritize those really interesting cases. And there's a few heuristics in QEMU for that. For example, inputs that run really quickly or inputs that are short. Then AFL++, again, integrates very well with QEMU. So that's a big part of it, that you don't necessarily have to run it with code that you compile for AFL. You can just give it a whole binary and it will still be able to know what to do with that because of its QEMU integration. And at the end of the day, what the QEMU integration does is it crashes, segmentation fault, for example, then AFL knows this is a crash. Again, you're just trying to run a program and see whether it crashes or not, and AFL just does that for you a lot per second. And for outputs, or for the behavior that a program exhibits once you feed it something, there's two cases. So there are the interesting cases and there are the crashes. So interesting means, hey, this firmware has done something that it hasn't done before. And for crashes, it's, hey, it crashed. That's great. Let's go get that CVE. And of course, I would like to mention that there's alternatives to using QEMU user space emulation together with AFL++. Two of them are called Firmadyne and FirmAE, and they both have their benefits and drawbacks. Both of them try to be a more complete solution to emulating the firmware on your computer, so you can think of it more as a virtual machine as opposed to just looking at a single part of the firmware. For my purposes, that's too complex. I would like to run something lighter so that I can focus on just one target. So, speaking of the target, once you start your security assessment and would like to do some fuzzing, you have to know really well what you're working with. So what I brought today is the TP-Link TLWR841N. It's pretty cheap. On Amazon, I think it was around 2,600 yen or so when I bought it. It has a 4-star rating, so can't be that bad. There's the PSK, please don't connect. And it's always good to know what version you're working with. So version 14, for example, that's the hardware revision. This is extremely important for especially the bug reporting part, because makers will suddenly decide that, well, version 13 is not supported by us anymore, so it's your fault for using it. But version 14 is actually the most recent one. Once you open it up, there's this green thing, the PCB, and it has a few components on it that we're interested in, including the system on a chip, the CPU, where you have the MIPS CPU, and we have RAM and flash. And again, I like to be very methodical about those things, take notes everywhere I can. So we look at the SoC. It's from MediaTek. They call it not an SoC, but a ROC, R-O-C, router on a chip. And that thing is very complete. So you'll see that there's only 3 components on this PCB. There's nothing on the backside. And it provides all the functionality for this router, including the Ethernet ports. It has 2 Wi-Fi radios. It's really interesting that things are so highly integrated nowadays. So you take note of what CPU, or SoC in this case, it has. This is the SD RAM. It helps if you know how much RAM it has. And this is the flash right here. So yeah, I just write down all the numbers. I try to find all the data sheets and just understand what I'm working with. To sum it up, these are the facts about the thing. And I think what's most important here is that this is the most recent hardware revision, and it's the FCC ID, meaning in the USA, there's a regulatory approval that you have to go through for devices that use they emit radio frequencies that have radios, and in this case, like there's an FCC ID. I don't want to open this. It's written down right here, and the approval date here means like this is when the FCC said, yes, you get our seal of approval, and now you can sell it in the USA. So there's just a bunch of things that you have to figure out before you start working with your target. It will make your life a lot easier. So then let's talk about the firmware. So as for the firmware, one of the best things you can do if you're working with an embedded target like this, and it's a router with one of those administration pages, you just log in, note the firmware version. That's good to know. Then you can go to the manufacturer's website, maybe see, are you using the latest firmware? Yes, no. If you're not using the latest firmware, maybe you want to update because maybe if you ever find a vulnerability, perhaps they've already patched it. So what I've done then is I've extracted a dump of this firmware. And if we go back here, this is the flash chip on in this device, and it stores the firmware. So you can extract the firmware. What I actually did is the UART console was not locked down, so I just took it out via TFTP. So I don't have a good time with chip clips, to be honest. I think I'm cursed in some way. They never work for me. So I usually just try to extract everything over TFTP. So what you do is you connect to the thing, and you're also connected through the network. So you just give it commands to send you things via TFTP. And if you combine that with tar and you do some bash one-liners, you can just dump all the firmware. It's very useful. So one of the most important things to know about your device, what you're working with, is the C library. In this case, uclibc version 0.9.33.2. Well, anyway, what's a C library? I think C libraries they do a lot of work without ever anyone noticing that they do so much. But if you have worked with C, if you've programmed something in C, then you'll probably know the C standard library functions. So like opening a file is called fopen. But also the C libraries are the gateway to your operating system. And this is where almost any program that you're using is interacting with a C library in some way. Even some like Rust would rely on a C library because the C library gives you access to operating system functions. And if we're working with Linux or other POSIX compatible operating systems, then there's functions called open, socket, and hundreds. And see the difference here between fopen and open, because it says fopen, like I know, yeah, this is a C standard library function. With open, it's, yeah, this is a function from Linux, for example. And then another really important part of a C library is the interpreter. Something that you will also know as a linker, loader. It's the thing that makes your program runnable if it has to load it in shared libraries, for example. And this is also a really important thing that if you don't have the C library, most programs will not run. But there are exceptions to this. If you have static binaries, meaning binaries that do not rely on any shared libraries, including a C library, they will not require an interpreter. And knowing about the interpreter is important, as we will see. Another thing that's useful to note down is the Linux version. Old kernels have vulnerabilities that the maker probably does not bother patching. In this case, we have Linux version 2636, which maybe you know how old it is. To sum it up, firmware version 14, this is the hardware revision right here. They just call it 241230, meaning December 30, 2024. At the time of testing, this was the most recent firmware release. Linux, you have 2636, and then uclibc, you also have something old. What's really important here to note is that the firmware release, at least in Japan, was in 2025. The Linux kernel was released in 2010. UC-libc is from 2012. And, well, I mean, if it's great software and it's not broken, there's nothing bad about that, but there's many known vulnerabilities for old Linux kernels. And what I think is even more critical in my mind is that UC-libc itself is not maintained anymore. And it's not, they're using the last release of UC-libc from 2012. There is something called UC-libc NG, which fixes a lot of open and security vulnerabilities that are in UC-libc. They're not using it. So if you do anything for embedded, please use UC-libc NG. If you find old code examples that say like, hey, use UC-libc, please don't use it. Use UC-libc NG. That's the currently maintained version, and then you won't have any issues with vulnerabilities. In my case, I'm not really looking for Linux or C library vulnerabilities, though. I'm more interested in the firmware that this vendor, TP-Link, has written. A little bit about MIPS-32 for those that don't know or want a quick refresher. So MIPS-32 is a specific version of the MIPS instruction set. It's very much like ARM, meaning it's a reduced instruction set computer, RISC. And that means there's fewer instructions than x86, but there's still a lot of instructions. This MIPS CPU is also very interesting because it's not little or big endian. You can configure it to be either. I actually don't know if ARM is like that, but maybe you know that some CPUs just need you to write everything in little endian or big endian, like PowerPC, big endian, and so on. Another thing that I thought is rare, that I haven't seen before, is that it has 32 general purpose registers. Now, of course, if you're writing applications for Linux, there's certain expectations for those registers, how you use them. And another thing to know, I'm just listing off facts here, but I didn't know about most of them, so it's good to know. They're called register architectures, ARM and MIPS. And again, that's more of a RISC-like thing right here, because for those who are interested, with your Intel CPU, for example, so x86, you can do complex operations where you operate on registers and memory at the same time, whereas with these very lightweight CPUs, you can't do that. You can only work on register values, and then if you want to put something into memory, you have to do a store separately. So the x86, for example, it has a lot of features that make code shorter, but I'm not sure if it makes it faster, but there's a fundamental difference in how they work. So this is called register. So this is another thing that, I see MIPS as a red flag because, well, MIPS is more commonly featured in cheaper devices. And I tried to find some hard facts, whether MIPS is still relevant, and I completely forgot about that time MIPS was part of the PlayStation. But anyway, the MIPS intellectual property changed hands a few times, and I think they've mostly given up on doing actual MIPS. Now they're doing something with AI. And then my analysis of this would be that if your CPU isn't very popular, you don't get great tooling. It's, for example, impossible to get a Rust toolchain for MIPS. I've tried, and I think some people are able to do it, but I didn't. So what that means in turn is, if you're a developer and you have to develop for something that's not well maintained, well, I personally would not be very motivated to do my job. So there's also this implicit assumption that you'll find more vulnerabilities, because if it's not very maintainable, tooling isn't great, then adding features alone could be difficult. So we've looked at the hardware, we've looked at the firmware, and now we want to get started. Is everyone excited? You all look extremely excited. I'm glad, because now we're going to learn how to use all of those facts and create a mock environment so that it can run on any computer. Linux computer, that is. So our target right now is the web interface, because that's usually juicy. They have a really big attack surface. There's a lot of things happening. Usually you can change almost anything about that device using a web interface, so that's usually where you want to get in. And the fact that if your router is misconfigured and you can access things from the internet, that means if you find a vulnerability, this vulnerability is network exploitable. That's cool. Maybe some of you know about Shodan, this website where you can look for open ports on the internet. I've already looked for it, and I think I found some, but yes. So one of the things you always want to do is just really basic research, like what type of file is this? So we want to fuzz the web server, so we look at this binary right here from the firmware dump called userbin httpd, and we run this command file on it. It gives you some really basic facts. It's always good to start with basic facts and then move on to the more advanced facts. And this confirms everything that we've seen so far. This is for ELF, it's 32 bits. And oh yeah, one more important thing is that the interpreter here is specified as UClibc, meaning that this program relies on this operating system having UClibc on it in order to boot up. And the first thing that I tried is just feed it to QEMU MIPS-EL. That's the command that you can use to to do user space emulation in QEMU. And you just run it like this. You give it the binary name and you just say, please run it. Well, what happens? First of all, it would complain, I can't find my interpreter. So I'm running it in some completely random directory in my home directory somewhere, and it has a hard-coded path that starts with a /lib. So it will look in your operating system for this shared library to load itself, and it won't be there. And even if it was there, your operating system will probably not be MIPS. If you're using MIPS right now, that's great. Like I've not heard about MIPS workstations in a really long time, even though they were big in the 90s. So you will just not have this interpreter. But there's a solution. QEMU has this flag, -L, that tells it, if you're looking for an interpreter, look in this directory. And you can also do the same thing with an environment variable right here, QEMU LD prefix. It always helps to look at manuals and to help. So we tried. This is my current directory. I unpacked a tar archive containing the whole root file system, and I just say, hey, find my interpreter here. So we try to run it. It should work, right? After all, it should find all the shared libraries and everything here. Turns out it doesn't quite work. And here's the part where it relies on external state, meaning state that is not part, functionality that is not part of the HTTPD library. So you get a bunch of errors, and one of the errors that immediately stood out for me is shmget failed. I have not heard about shm before, and we'll find out what it is, because we're very diligent and we do our research. After about 2 months of wrestling with this, trying to find out why it doesn't boot, I came up with a very detailed picture of all the things that it has to do. I made this small and imposing on purpose to make everyone, including me, tremble at the amount of environment mocking that you would have to do. You have to do a lot. To put it in a list, there's the following thing happens. So many operating systems have some kind of process that starts as the first process. This is usually called the init process. TP-Link wrote their own init process, and this init process, it doesn't just launch all the other binaries, it does much more. As a matter of fact, it uses a very old API from the Unix system V days to, first of all, read configuration from the flash and put it into shared memory. This is not memory mapping, like mmap, but it's shared memory. Then it starts HTTPD, which is the process that we're interested in fuzzing. And it, well, gives it the configuration through shared memory, and HTTPD is like, great, now I know all my configuration, like which port I need to use and so on. But still, I want more. I want you to tell me that I actually have to start. If you don't do that, if no one tells it to start, it will just never start. So through intense reverse engineering over a long period, I found out that you have to send it configuration messages over a Unix domain socket. And we'll see how that looks like in practice. So it then receives these configuration messages, and only then finally does it start on your own computer. That's great. One of the things that you always try to do, again, basic research, we want to reverse engineer all of this behavior, and there's a lot of external state that it relies on, shared libraries and so on. There's so many useful commands that you can use, and one of the commands that I highly recommend for this kind of reverse engineering is a program called patch-elf, which just prints out the shared libraries that a program relies on. And why do I recommend patch-elf over anything else? Well, I'm a big Nixos user, and it's very commonly used there. And also one of the advantages of using patch-elf over, for example, LDD is that with LDD, it, as far as I understand, runs the program. So you can't really do it on untrusted binaries, versus patch-elf just tries to parse the syntax of an ELF file in order to find out what shared libraries it relies on. And then our overall strategy, our overall strategy is to then mock all those functions and create a shared library with that and inject that into the process. So we have to do three things. We have to find all the functions that it relies on. We mock them, make a shared library, and then using this environment variable right here, LD preload, we tell the UClibc interpreter, you should prefer our functions. And I'm going to abbreviate this a little bit, but I had to do a lot of research for this. Again, I wasn't familiar with a lot of commands or APIs, but also there's so much external state that it relies on. So you start doing your research. The manual is great. You learn a little bit about this old system VIPC, and you just try to find the functions that it relies on. Then you have to define, what do I need to add into my own C library? And that's the one part, but then there's the part where it uses TCP to receive your HTTP requests. For that, you have to know how Berkeley server sockets work. So there's a whole state machine behind that you have to emulate with high fidelity as well. You have to list up what the functions are that you have to mock there. You have to know a little bit about what kind of sockets are there in the first place. There's just too much. I don't think you should implement all of this unless you have a lot of time. So what you try to do is you reverse engineer the program. You try to identify what sockets are you interested in. You might not be interested in everything. Maybe it opens other ports that you don't want to intercept. And then in our code, in this library that I'm writing here, I mark all those sockets as, hey, this is the TCP socket that I'm interested in. Or maybe if it's reading something from the flash ROM, that's something that I'm interested in. And then you start writing code that almost looks like operating system code, like from the C library. So I would, for example, define a function here, socket. So instead of the operating system function called socket, it would start calling our socket instead. And then we try to see what kind of socket does it want. And if it's creating an HTTP port 80 socket, that's the one that we're really interested in. So this one we're just going to mark as interesting right here. And the same for this configuration socket that receives the configuration messages, we mark it. And now the final thing is, now that we've mocked all of that, it will start, but we haven't done enough. Now we want to be able to feed our own naughty requests using standard input. So what you can do there is you just connect the TCP end into the standard input end. Just a quick refresher, standard input on Linux and many other operating systems, your program will start with 3 standard streams. And standard input is just one way that you can give it text so that it can do something. If you have used a pipe in bash, you rely on standard output, standard input. And for fuzzing purposes, again, we want to go fast. This is better than working with sockets because setting up sockets takes so much more time. So then here is I'm going to briefly show the code where we hook the standard input into the TCP receive bit, because at some point when you want to read something from TCP, you call this receive function. So we just say, oh, hey, we've marked this as interesting. Let's do our own receive bit here. Does anyone know what message peak means in TCP? Oh, yeah, I don't know about it either. So there's an interesting thing about TCP sockets that surprised me. You can peek ahead a few bytes. For example, you want to see, do the next few bytes start with HTTP? So you can peek, and then it's as if you haven't read them, versus using read, the OS function read, it advances the pointer inside the file, but with peeking, it doesn't advance. I didn't know that, and it, well, cost me a lot of time. But of course, the manual has you covered. I should have just looked it up, obviously. So we handle this extra peek case, and oh, finally, now we're reading from standard in. And again, you shouldn't have to implement all of this. I highly recommend for your fuzzing, use something called libdsoc. It's great. It does most of it. I just needed some more customization, so I wrote my own thing. So then we have to cross-compile it, meaning we have to make it work not on our CPU and our operating system, but on some other operating system, so that's why you have to use cross-compilers. And Nix makes that really easy. You can just say, hey, I want this cross-compiler. And oh, by the way, I also want to run GDB on that machine, and it should be a static binary, and it does all those things for you. It's great. There's also some snippets that you should always have ready. Like with Nix, I can just say, hey, I want GDB, and then copy it over with TFTP. And then on that machine, you can just run this right here, and suddenly you have GDB looking inside the web interface. Very powerful. So then after you've made all of this, there's some environment variables that you can give to QEMU to tell it, please use my interceptor library. Now the third part, that's where you configure the fuzzer. So again, AFL architecture is all about giving things to QEMU and then looking what the output is, whether you get a crash or you get something that you haven't seen before. So the 5 parts, as I said before, we have the mutator, which we can't influence, but we have everything else here, the scheduler, how fast can we run things. That's why we're doing all of this. And yes, it's fast, I promise. But the problem is, where do you get the test inputs? So what I've started doing is, maybe some of you use Burp, I use MITM proxy a lot. I just use the web interface and I just dump out all the HTTP requests and then use that as my test corpus. So the test corpus, that's the initial test cases that AFL uses to, or AFL++ uses to generate the naughty strings. And here's an example. This is in one of those text files. It looks like an HTTP request, and it's an HTTP request. There's some tricks to making your corpus better. If you're interested in that, talk to me later. There's some good tips there. And it goes even faster if you launch AFL++ on multiple cores, because it doesn't do that automatically for you. So again, you can start doing a lot of bash scripting for this. In this case, I'm using some for loop right here to launch a main, well, I'm launching a main AFL++ instance, and then I'm making a lot of secondary instances right here, and then they all work together and fuzz really fast. There's so many tricks. I just want to briefly show, if you don't do the tricks really well, it runs very slow. But then when you do a lot of tricks, suddenly it runs very fast. And I've tried to benchmark this a little bit. Fork server, that's another feature that just makes it a lot faster. We can go from really slow to more than 100 times faster. So that's great. So we found a crash. Wonderful. The thing crashes. And it happens when you send this request. So what's happening here? Apparently, if you start a refer with HTTP:// and that's it, it just crashes and freaks out. So we can, because we've emulated it, we can also just reproduce that locally, but we can also reproduce it on this machine. It's good to have a lot of crash dumps for diagnosis. And, oh, right, I have to give a live demo. Great. So we have the thing here. Can you please crash? No. Oh, this always happens. No worries. I've got a backup. There we go. So on the right side, it loads just fine. We send the nasty string, the one that you saw, and oh, it's down. Too bad. Woo! Thank you very much. Wonderful. So let's wrap it up. Oh, this thing is online right now. Has someone crashed it? Well, I don't know. Anyway, so here's the PSK if you want to try it out. If you see the SSID, have a go at it. You can use GDB to debug those things. QEMU makes it really easy to hook GDB into it. So you can reproduce it on your own machine. It's wonderful. Once you start emulating everything, you're omnipotent. We look at the stack trace right here in GDB. It tells you where it crashes. I looked a little bit at the code, and there's a null pointer passed around here. So this is more or less where it stops working correctly. It's something about trying to turn your IP address into some other information. And this is exactly where the crash happens. Wonderful. So this is the blueprint to fuzzing. You find out what you're working with. You look very closely at the firmware. You create your test corpus with all those nasty inputs, and then you start fuzzing. This took me around 180 hours. Most of it spent on just reverse engineering the firmware, which it's really boring to talk about because it just takes so much time, and then you just know how all the functions are called. But it just takes so much time. I also spent some time on contributing patches to AFL++. Great project. I've received a CVID a few months ago, but it's still embargoed, so TP-Link just won't publish it. But here I am talking about it anyway. Woo! That's it. TenguCon 2.0 rocks. That's what you can do when you reverse engineer things. You can change strings. Thank you very much. Thank you very much.
All right, let's hear it again for Justus.